A client met his banker to discuss opening a restaurant in a busy airport. In us, he found a partner that understood the importance of reaching for the sky. First Horizon Bank. Let's find a way. Go to firsthorizon.com/Mac. Recently, our client John met his banker to discuss plans for a clean energy building. What he found was a shared passion for building something more. Momentum for change. First Horizon Bank. Let's find a way. Go to firsthorizon.com/John.
15 seconds. Guidance is internal. 10, 9. Ignition sequence start.
Space Nuts.
5, 4, 3, 2.
1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
Hello once again and Happy New Year. Thanks for joining us on the latest episode of the Space Nuts podcast, episode 235 is what it says on there. Notice the professional rundown sheet. No, it's all backwards. Anyway, I'll have trouble reading that. My name is Andrew Dunkley, your host, and joining me as always is the good Professor Fred Watson, astronomer at large. Hello, Fred.
Hello, Andrew. Happy New Year. I wanted you to see my astronomy face mask that my daughter sent me for my birthday at the end of last year. It's got all the constellations on. Sadly, they're all in the wrong place, but they are the right constellations. They're the real thing. So this is my new fashion accessory, which I don't need in here because I'm on my own. The nearest person is 20 metres away in a different room, so I'm going to take it off. But I thought you'd like to see it.
Yes. That's a beauty. I love it.
It's good, isn't it? Yeah, it's great. I like that too.
Yeah, very clever. Actually, I've seen a lot that people have been creating. You've got to give humans credit for their ingenuity. That some of the face masks that have started popping up around the world just are so imaginative. I'm not so sure about the zombie ones because I think they'll scare children.
Yeah,
but some of them where you look like you're a skull and.
I've got another good one to show you in a later episode. So that's one I haven't worn yet, but I've seen it, so that'll be good.
Yes. And by the way, how was Christmas and New Year? What did you get up to?
I wrote 2 chapters of the new book, and I'm still forging ahead to try and get the text out the way as soon as I can, so I can start on the cartoons for it because that's the next big thing. Yeah.
Oh! Just don't go away. This is so impromptu. Hang on.
He's gone. Ladies and gentlemen, that was the late Andrew Dunkley, who's just revealed his chest full of, his bookcase full of trophies. Here we go.
Hang on. It's done.
Is it? Oh, the book's done.
Yes.
The Hitler Paradox. What a title.
So that's ready for my proofreader. So we're all good to go.
Good to go, yeah.
It's a hard copy.
Yes, hard copy.
I need an editor. I need a proofreader, an editor, and a miracle. So,
well, miracles happen.
Anyway, that will be out sometime this year. Probably the same day as Fred's.
Yeah. Oh no, that's not till October. Mine comes out.
I can wait.
Yeah, oh, good.
No rush.
Your fans can't though, Andrew. Fans will be.
Yep, yeah. Both of them.
Yes,
that includes me. That includes me. Now, we better get down to business. So, New Year was good, Christmas was good, ours was good, very, very quiet. So, we didn't get up to much. Not that we could because there were so many restrictions that we had to deal with because of the Sydney outbreak. But, hopefully things will get better this year. But that's a wish against a wish, I think. So in this episode of the Space Nuts podcast, we will be talking about Earth spinning faster than it used to. That's because people are running a lot faster than they used to, and the planet's sort of like treadmill effect. It's true. Chinese astronomers, we've got a lot of speed going on. Not the wrong kind of speed. We've got a lot of speed going on in this week's episode. Chinese astronomers find nearly 600 high-velocity stars. That's because most of them are 17 years old. Now, and a couple of questions coming up. One from Tom in the Midlands of the UK around Benford's Law, which this fascinating question. And Daryl in South Australia has a what would happen if question for us. I love those ones. So we will deal with all of that today on the Space Nuts podcast. Now, Fred, to our very first topic for 2021, Earth is spinning faster than it used to. Someone suggested the treadmill effect. I suspect otherwise.
Actually, the treadmill effect is as good a guess as any, because at the moment, nobody knows why. So, yeah.
Oh, well, that was a short segment.
Yeah, it's a theory that, is, it should go into the mix for what the reason is for this faster spinning Earth that we're seeing. And it sort of flies in the face of the normal wisdom about the spin. We've known ever since the invention of atomic clocks, and probably a little bit before that, actually, but we know that the Earth's rotation is not constant. It's a very poor timekeeper. It's sort of, and it's because its spin is affected by things like the sloshing around of the liquid iron core in the middle, or the solid iron core in the middle and the liquid iron core above it, and the, the convections in the mantle. But it's also affected by other things like melting ice sheets and ocean currents and things of that sort. All of those things affect the rotation of the Earth. But as you and I have spoken about before, Andrew, the normal way it changes is by slowing down. And that's because of the tidal friction effect between the Earth and the Moon. The Earth is gradually putting energy into the Moon, which makes it recede away from us. And that energy has to come from somewhere. And by and large, it comes from the slowdown of the Earth's rotation. But it's not just a constant drift downwards. It's got bumps in it. And we had a bump effectively last year. 2020 apparently had more short days than we've had for quite a while, which means that the spin is going up. Sorry, Andrew, go ahead.
I knew that last year felt quicker. Everyone said, how fast did 2020 go?
It went like a rocket. That's why, yes. Well, the shortest day was, but by day now we don't mean daylight or anything like that. It's the standard day is 86,400 seconds. That's how many seconds you've got in a day, which is 24 times 3,600, the number of seconds in an hour. So the shortest day was actually July the 19th last year, the depths of our winter down here in Australia, but high summer up in the Northern Hemisphere. And so that 86,400 seconds was short by 1.4602 milliseconds. So it's not really something you'd notice, but it is a short day.
Blink and you would miss it. Blink and you would miss it.
You definitely miss it. Yes, blinks are usually longer than a millisecond, so you would. But yes, there's no. So I should say that nobody's worried about this particularly. It's just a reflection of the fact that the Earth is, is variable in its spin, and exactly as I was saying, things like the movement of material within the Earth, but also I think to some extent we're seeing the sensitivity of the Earth to what actually happens on the surface, and that's because on the surface there's effectively what's called a bigger moment of inertia, so that things that happen on the surface actually have a bigger effect, and that's why just the level of snowfall, for example, over a continent like Greenland or over an island like Greenland, and even things like the erosion of mountains by glaciers and that sort of thing, all of these can change the speed of the planet's spin. The other side of it, and maybe this is a little bit more concerning, is that atmospheric and climate scientists are looking at this as perhaps us seeing something like the effect of global warming, where you've got snow caps melting and the snows high up in the in the mountains actually disappearing. So it's really, it's an interesting yardstick, and it may mark the beginning of changes in the way the Earth rotates. Now, the people who are really most upset about it are the computer scientists, and they always are, because that's why computer scientists hate the fact that the Earth's spin is gradually slowing down, because in order to compensate for that, we introduce leap seconds periodically. I think there's something like 30 been introduced since 1975, was it, the first time a leap second was put in. But their computers need to be adjusted if you put a leap second in. And that's a big pain in the neck, because it's on, systems on board spacecraft. It's all over the place where things have got to be changed. And the idea of the Earth speeding up a bit could mean that you put in a negative leap second. That's to say, you take out a second at the end of a 6-month period. It's either the 30th of June or the 30th of December that these are put in. So you could take one out. And that, again, could lead computer scientists to tear their hair out and have all kinds of problems. So they're the ones who are most directly affected by this. But I thought it was a really interesting piece of research to point out that actually occasionally the Earth's spin speeds up.
Yes, it is. It's fascinating. I believe the first leap second was added in 1972. You weren't far off. And, when the Earth slowed down a little bit, and there's been, I think, 27 leap seconds all up thereabouts. I did have a question. You mentioned at the beginning that the tidal effect of the moon is supposedly slowing the rotation of the Earth, but we also know the moon is creeping away from the Earth and will over time go. Will that change the spin of the Earth as it moves away, or is that too slow an effect?
The two are intimately linked, Andrew. And the moon will never disappear. It will settle down about 500,000 kilometres away. This is in something like 50 billion years. It's nothing to worry about. But it's actually, so it's the gravitational interaction between the two that causes both of those phenomena, the slowdown of the Earth, which is because it's giving energy to the moon. It's a fairly complicated process, but it's all about the way the tidal bulge on the Earth actually acts gravitationally on the moon itself to give it an acceleration, and that acceleration moves it further out in its orbit. So yes, two intimately linked processes, both of which are very interesting, I think. Excuse me.
Yes, they are. The other, you mentioned the bulge. I actually looked it up once, and I think we have talked about it once or twice. The bulge is responsible for quite a significant difference between the width and the height of the planet. It's quite a large variation.
That's the equatorial bulge. Yes, the bulge caused by the spin.
Equatorial bulge. Sorry,
yeah, there's too many bulges here. Actually, something that staggered me, Andrew. The Earth has an equatorial bulge. It's fatter around the middle, as are pretty well all the planets. Saturn is the most. Saturn is 10% wider across its equator than it is at the poles. But wait for this. In the all the research that I've been doing for the kids' book, one of the amazing facts is how perfectly spherical the Sun is. So the Sun is 1.3 thereabouts million kilometres in diameter, and yet it's the difference between its equatorial diameter and its polar diameter is less than 10 kilometres. It's staggering. So it's absolutely a perfect sphere, which is really quite remarkable.
It is. So here's another question without notice. I'm getting good at that. If the Earth was spinning a bit faster in 2020, does that mean the equatorial bulge, got a bit bigger?
Yeah, it probably, but the amount. Yes, it would be about a millimetre or something like that, probably. Exactly.
Well, that's too much. That's about 10 millimetres.
Yeah, that's too much. That's an overestimate. So it's
it's just a guess. Okay. I think we got that covered. Great topic to start off the year too, I might add. Yeah, fascinating.
Yeah, I thought so.
You're listening to and occasionally watching the Space Nuts podcast with Andrew Dunkley and Fred Watson.
Tonight in Arkansas, there's a mother tucking in her daughter and turning off the light. A business owner is burning the midnight oil. An at-home dinner date is plating up possibility. And it's all happening under one roof. How? The power of a conversation, like the one John from Integrity Solutions had with First Horizon Bank about his vision for a sustainable mixed-use building. Now it's not just words, it's life. First Horizon Bank. Let's find a way. Go to firsthorizon.com/John. First Horizon Bank, member FDIC.
Roger, you're loud and clear here also.
Space Nuts.
Thanks again for joining us on the Space Nuts podcast. Andrew Dunkley here with Fred Watson. And thanks to everybody who send questions in to us, because we like to get questions from the audience. We feel it gives you a bit more to enjoy. It's not just us rabbiting on about what we like to talk about. We get to talk about the stuff that you want to know about as well. And we've got episode 240 coming up very, very soon. And as we tend to do on the rounded numbers, we offer the opportunity to go all in. So if you've got a question buzzing around in that massive brain of yours that you would like Fred to tackle, please send it in to us. Just go to the Space Nuts podcast website. spacenutspodcast.com is what it is, coincidentally, and you can upload your question through our email interface if you don't want to use your voice, or you can click on the AMA tab and record your voice. As long as you've got a device with a microphone, it should work, and just tell us who you are, where you're from, ask your question, bam, and away we go. So we'd like to do an all-question episode for episode 240, which will be coming up in about 5 weeks' time. Now, Fred, we have got the need for speed in episode 235 of the Space Nuts podcast, and we go from a faster spinning Earth to high-velocity stars, which have been observed by the Chinese, and they've found quite a few of them.
Yeah, that's right. This is actually a story quite close to my heart, Andrew, for a number of reasons. Partly because I've been involved with work in measuring high-velocity stars myself in the RAVE project, the radial velocity experiment, which we did with the United Kingdom Schmidt telescope during the first decade or so of the new millennium. We surveyed the speeds of 500,000 stars. And one of the first pieces of research that came out of that was the detection of high-velocity stars, nothing like as many as the Chinese astronomers have now discovered. But what that does, it's not just that these are stars that are leaving the galaxy and you're waving them goodbye. It actually gives you a way of measuring the mass of the galaxy. And we got a mass for the galaxy from those results of, if I remember rightly, it was 1.4 trillion times the mass of the Sun. That's a result that actually still holds up, I think. Anyway, things are moving on because with a telescope, which again I've had quite a bit to do with, it's called LAMOST. It is a telescope that is built, it's actually only about 100 kilometers from Beijing for reasons that I won't go into here, but it's on a site that is rather light polluted, but is very good for observing relatively bright stars. And what they've done with LAMOST, and its name is actually an acronym. It is the Large Sky Area Multi-Object Fiber Spectroscopic Telescope. And there's the clue, because my career was all about multi-object fiber spectroscopy, which is where you use optical fibers to steer starlight from the telescope into the spectrograph, the device that actually turns the light into a spectrum and lets you analyze all its details. So our fiber spectrograph on the Schmidt telescope had 150 fibers when it was in good condition, but the LAMOST telescope has 4,000. So it can look at 4,000 stars simultaneously. And that's why they are doing now very big surveys of star speeds and the chemistry of stars as well, which is one of the other things that comes out of this. So the study that's just been published has now a total of 591 stars added to the list that we knew already, which was about 550. So it kind of effectively doubles what we know. Often these stars are ones that have actually had something happen to them. For example, if you have a star that happens to be in the center of our galaxy and wanders close to the black hole near the centre of our galaxy, it might get caught up in that maelstrom of material, but not quite be sucked in, but in fact given a kick outwards to give it these very high velocities. It's that sort of thing. Or even just an encounter of two stars coming together where they don't collide, but the gravitational interaction actually boosts one of them out of the galaxy. So it's really, it's a really interesting piece of work. But today we have something we didn't have in the era of RAVE, the radio velocity experiment. We now have the Gaia spacecraft. And what Gaia is doing is measuring very accurate positions of stars. They're accurate to something like a millionth. It's about 5 millionths of an arc second. A tiny fraction. A second of arc is 1/3600th of a degree, which is a relatively small angle. But then they're splitting that up to millionths of an arc second, and that lets you look at the way stars move across the line of sight. When you can combine that with the radial velocity, which is the velocity along the line of sight, you get the true space velocity of the star, its actual motion through space, and that's how you can deduce that some of these are very high velocity and are effectively leaving the galaxy. It's great stuff.
How fast are we talking?
I don't have figures, but because I haven't actually had time to look at the paper itself, which came out on the 17th of December. But the typical sorts of figures that we were talking about with RAVE were of the order of 400, 500 kilometres per second. And that's enough to get you out of the galaxy. It's all about the escape velocity of the galaxy. And that, of course, varies depending on whereabouts in the galaxy you are. So it's not a single number. And I think we used to quote the escape velocity at the sun's radius, and I can't remember what the number is. I could probably look it up, but I won't do it just now. I think it's less than 400 kilometres per second, but you get the drift. These are velocities in the region of a few hundred kilometres per second.
How fast is our sun moving, our star?
So we are part of the sort of circulation around the centre of the galaxy, and our speed is round about 250 kilometres per second. And that's the sun's orbital speed around the centre of the galaxy. And in fact, because of dark matter, that's the orbital speed of most stars. One of the reasons why we think dark matter is there is because of this, what's called a flat rotation curve. When you look at galaxies, everything's moving around at about 250 kilometres per second, whereas what you would expect is for the velocities in the middle to be fast and then for them to slow down as you go further out, but they don't. And that's one of the reasons why we think every galaxy is encased in a cocoon of dark matter. It's perhaps the most significant reason why we think dark matter is real.
Someone's going to ask the question, if everything's moving at approximately the same speed, then how is it all drifting apart? But I suppose it doesn't matter what that speed is. You're drifting outwards, therefore apart.
Well, do you mean the expansion of the universe? So that is much, much smaller and only comes into play where you've got huge distances. We're talking about galaxies which are bound by their own gravity, and that sort of overrides anything to do with the drift of space, which is much, much slower. It's the values on the scale of a galaxy, the expansion of the universe is zero. It's only when you're looking at galaxies that are separated by millions or billions of light years that you start to see the expansion of the universe.
Okay, makes perfect sense.
Good, I'm glad it does.
You mentioned a few reasons why stars reach these higher velocities. The one you did mention is that they just got their driver's license.
Well, we know those because they've got a P attached to their.
They have. Well, in the state of New South Wales, and I think in a couple of other states in Australia, people who just get their licence have to demonstrate so with a red P for their first year, provisional licence, and then I think for 3 more years or 2 more years, they have to have green P plates. Yeah. So they're well identified. It doesn't slow them down at all. But yes,
I think you're making generalisations there, Andrew. Because
I'm not blaming all of them. I'm not blaming all. Only 90.9% of them.
I know some former P-platers who were very, very careful indeed and never went fast.
Yeah.
And I'm their dad.
Yeah, my boys were pretty good too.
Yeah, but anyway.
It comes down to the teachers, doesn't? No, let's not go there.
That's not good.
All right, time for a break. Here on the Space Nuts podcast, episode 235, you're with Andrew Dunkley and Fred Watson.
Well, shopping for a car?
Yep, Carvana made financing a car as smooth as can be.
Oh, yeah?
I got pre-qualified instantly and had real terms personalized just for me.
Doesn't get much smoother than that.
Well, I got to browse thousands of car options on Carvana, all within my budget.
Doesn't get much smoother than that.
It does. I actually wanted a car that seemed out of my range, but I was able to add a cosigner and found my dream car.
It doesn't get much...
Oh, it gets smoother. It's getting delivered tomorrow.
Visit Carvana.com or download the app to get pre-qualified today.
Okay, we checked all 4 systems and skiing with a go.
Space Nuts.
This is the Space Nuts podcast with Andrew Dunkley and Professor Fred Watson. And a special shout out to all our patrons, of course, who put a bit of money into the podcast. We certainly appreciate your support. And if you'd like to become a patron, you can look up the details on our website, spacenutspodcast.com. You can give a little, you can give a lot. It's totally up to you. It is not mandatory. I must point out. And a shout out to our social media supporters, those that follow us on Facebook, Twitter, where else? Patreon, yes, I suppose you call that social media. There's also Pinterest and a few other places. What's that other one called? Instagram. I should know all this. I've got all these, but I just get so lost in them. There are so many. But and YouTube, of course. You call YouTube a social media platform, I suppose. But we're getting quite a following on YouTube. So thank you to the YouTube followers for supporting the Space Nuts podcast. And we get a lot of feedback from YouTube as well. So thank you very much. Now, Fred, we've got a couple of questions to tackle. This first one's... Yes, this first one's pretty wordy. This comes from Tom, who lives in the Midlands of the UK. Hi, Fred and Andrew. I have a question regarding a mathematical phenomenon called Benford's Law. I came across this a while ago whilst casually researching various things online. For those unaware of Benford's Law, it's an analytical tool commonly used to detect financial fraud. I find this fascinating, Fred. Basically, the law states that when taking the first digit of numbers in large data sets, the probability of each number 1 to 9 occurring repeatedly decreases the higher you go. For example, the number 1 will occur 30% of the time, 2 around 15%, and so on, 9 occurring just 5% of the time. Auditors then use this tool to analyse data sets and find anomalies in the information. If a company's data features a 9 as the first digit, say 16% of the time, providing the company's services don't offer products whose prices exclusively begin with a 9, that's important, it's a likely indicator of fraud. So now to the actual question part. In Benford's Law, is Benford's Law commonly used in astronomy to analyse things like distances between stars, galaxies, exoplanets, or for other large sets of data relevant to astronomy? I've read several articles that have explained how they've explored this law in nature for things such as depths of earthquakes, sizes of animals, and infectious diseases, but there doesn't seem to be a huge amount on astronomy and space. If this law applies not only to financial information, but much to the natural world and the universe, that would be somewhat intriguing. Love the podcast, discovered it 4 months ago. I tend to listen to it whilst playing a space exploration game, which really enhances the experience. I'm fully caught up and now have begun re-listening to some episodes, you poor thing. If you could start recording twice a week minimum, that would be great. Hope you're both well. All the best. Tom from the UK Midlands. Benford's Law. I like the sound of this. It's interesting.
Yeah, it was actually, and in fact, Benford was the second person to discover this law, because it was also discovered 50 years earlier, in 1881, by an astronomer by the name of Simon Newcomb, an American astronomer. So it's sometimes known as the Newcomb-Benford law. So astronomers have certainly looked at these numerical distributions. But Tom's right, actually, that it's not a tool that is widely used in astronomy, although I take his point that, other natural things have been used or have been shown to fit this law, like mathematical or physical constants. It's a really very interesting thing. I think financial fraud is probably its biggest use. But the point I was going to make is that in astronomy, there are statistical tools which are quite different from this and very much more suited to the problems that we face in astronomy, which are things like looking for trends in the metal content of stars in their atmospheres or their surface gravities, how they're distributed with distance in the galaxy. And for that, the kind of statistics that we use are perhaps in some ways more conventional, although the flavour of the month is still something called Bayesian statistics, which is a set of statistical tools that involve you effectively taking a guess at what the answer might be. So you fix something called a prior, and the prior is your starting point when you are going through the statistical number crunching to work out what the answer is likely to be. So Bayesian statistics play a much bigger role than Benford's law. It is interesting, though, how applicable it is over many different physical parameters. One of the things that I thought was an interesting consequence of Benford's law is lengths of rivers. And that's such an interesting thing, that the length of rivers actually fits this natural law. Just one other comment. I'm going to have to nip off for a second because my computer's got a red light on it that tells me I forgot to plug in the mains power. So I'm going to let you chat for a second while I go and get it. But the really interesting thing I think about Benford's law when you look into it is it works best when you've got statistical data covering many orders of magnitude. That means, tens, hundreds, thousands, hundreds of thousands, millions. If you've got data that covers that broad base, then the law works really well. If you're only within one order of magnitude, 1 to 10, then it doesn't work so well, which is an interesting aspect of what I think is an interesting law. I'm going to go before my computer dies, Andrew. I'll leave you to talk for no longer than about 30 seconds. Hang on.
Oh, okay. I think I can manage that. I used to work in radio. I'd still turn up for radio. I don't know if I work in it anymore. It reminds me of a trip Judy and I did a couple of months ago now. We decided it was only an overnight trip. We decided not to take our phone chargers. And, of course, my phone burnt its battery heavily. And so the next day driving home, we had a cable in the car. And I thought, okay, well, I'll just plug it in and charge the phone on the way home and everything will be apples. When I got home, the phone was almost dead. And I thought, what the heck? Over the course of time, the plug in the adapter in the car dashboard had worked its way out a couple of millimetres and no longer had contact, couldn't charge my phone. You get caught out in the stupidest ways, but luckily I got home with a fully functional phone. Although the latest update that I've put on my phone now causes my battery to burn daily, and it's a brand new phone, so I'm a little bit annoyed. And apparently the fix isn't going to be uploaded until next month. So yeah, I think a lot of these mobile phone companies have got a bit to answer for, Fred. I really do. But that's another story.
Well, thank you.
Welcome back, by the way.
Yes, thank you. Sorry about that. I didn't want it to die.
Oh, that's okay. Fair enough. Now, let's move on to our next question. And this is a what would happen if question. This comes from Daryl in South Australia. I must point out, too, that this question and the one from Tom, that they're patrons. But just for a change, we're including a couple of these patron questions in the mainstream podcast. Normally, they'd go into bonus material for the patrons. But these questions were so very good, we thought everyone would enjoy them. Now, Daryl says, the other day I was watching a YouTube channel And the title of the segment was, What Would Happen If the Earth Got Kicked Out of the Solar System? It was mentioned that some 70,000 years ago, a brown dwarf, red dwarf binary system passed through the Oort cloud and messed things up. It was also stated that Gliese 710, I've probably mispronounced that, will pass through in about 1 million years' time. So he's asked several questions. Have either of you heard about this? How do scientists now know this happened? Can this still be seen through telescopes today? How would it take? How long would it take for asteroids from the event? And how can scientists track something that might take 1 million years to be in our neighbourhood? Good questions. And over to you, Fred. I
love the way. You haven't heard of it. That's all right. I was just going to say, I love the way that Darryl has numbered his questions 1, B, 3, D, and 5.
I managed to avoid that.
It's quite nice. So, yes, I've certainly heard of Gliese 710, which is a star that will pass through in a 1 million years' time. I don't know about the brown dwarf, red dwarf binary system. It's possible that might have happened. So let's just step back and work out, what's going on here. The solar system is not just the planets and the asteroids and comets. It is also the Oort cloud, a cloud envisaged by Jan Oort, a Dutch astronomer, back in about 1950 or thereabouts. He postulated that the source of comets is this spherical cloud of comet nuclei, which are bodies a few kilometres long, very icy. But if you've got lots of them out there, a passing star could disturb the Oort cloud, propel them into the inner solar system, where they will essentially fall in towards the sun and be visible as comets, because once they get near the sun, they start evaporating there. The ice is basically turned to vapor, to a plasma, in fact, and then you can see them. But of course, if that happens on a wholesale scale, if you've got something that churns through the Oort cloud and disturbs it and sends a whole lot of comets into the inner solar system, there's a good chance that some of them are going to hit the Earth. And so people who look at asteroid impacts and things of that sort, and the history of the Earth in terms of mass extinctions and cratering and things of that sort, they are the people who I think would be saying, well, something happened here. We had a whole lot of impacts, mass extinctions. Maybe that was because something passed through the Oort cloud. And you can actually, this is going to one of Darren's questions here. B, I think, actually, not 2, it's B. How do scientists know this happened? You can look at stars now, especially that we've got the Gaia data set that we were talking about a few minutes ago, these exquisite positions of stars, which also give us the chance to work out their motion, how they're moving. If you combine that with radial velocities taken from a spectrograph, then you've got this, the complete motion of a star. And if it's, we can look at stars out there in the universe and say, well, or in the galaxy and say, well, this one would have been in our vicinity, a few 100,000 years ago or something of that sort. So that's how that kind of deduction is made. And so that red dwarf binary system, as I said, I haven't heard of that one, but if it really exists, then it probably is something that has been observed through telescopes. The Gliese 710 is much better defined, because that's one that's kind of on its way. It hasn't passed through the solar system yet. It's a red dwarf star. Gliese stars are essentially red dwarfs. They come from Gliese, Herr Dr. Professor Gliese's catalogue, and that's his number 710 in the catalogue. It is expected that there will be an interaction between Gliese 710 and the Oort cloud, because it will come in closer probably than the Oort cloud. It's 0.2 light years is its minimum distance. The Oort cloud is round about that distance from the sun. So this is an event that is expected to occur on our best figures in 1,281,000 years' time. And that, again, comes from the Gaia data. So it's a close approach, and that is likely to disturb the Oort cloud. And so one of the other questions that Daryl has asked, question D, how long would it take to see asteroids from this event? There would actually be comets rather than asteroids, because the Oort cloud is the reservoir of comets. They would take, yes, tens of thousands, hundreds of thousands of years to spiral in from the Oort cloud into the inner solar system, maybe on average 50 to 100,000 years. So it's not an immediate thing, but this star is itself kind of not an immediate effect. It drifts through the sky at a relatively leisurely pace. I think I saw a figure of 1 arc minute per year, I think was what I saw. It might have been, let me just see if I can pick that up again. It was certainly something that would be easily visible. It's a star that will be relatively bright. In fact, they were suggesting a magnitude of about -2, which is as bright as Mars gets when it's brightest. I'm sorry, I can't find that figure of its drift. But the star would be there, and it doesn't whiz through the Oort cloud and bash everything up. It's a very leisurely process. But the effect of this 100,000 years or so after the closest approach, when the star would still be visible in the sky, that's when you start getting the comets feeding into the inner solar system. And the last question, how can scientists track something that might take 1 million years to be in our neighbourhood? It's exactly what I've just said. It's looking at the information we get from Gaia and the radial velocity surveys. That gives us the space velocity of a star, and then you just map it forward, because there's not that much else happens in the in the period in our galaxy. You've got to look at any other stars that it might interact with, but 1 million years is, it's not that long in the grand scheme of things. So it's very interesting, a really interesting question. I'm very glad that Daryl raised that one.
Yeah, it's a ripper. Yeah.
Could be a ripper for anybody, any of us who are still left around in 1.28 million years.
Well, it's a question about the predictability. I suppose 1 million years out, that makes it a little bit of a lottery, doesn't it?
Only in the sense that you might have ignored or missed that there's a faint star somewhere between it and us that will disturb its path, and that the modelling that people are doing about the way stars are moving within our neighbourhood actually go out to 15 million years, and so there's certainly good modelling that takes into account what we know about the stars in our vicinity. And this one's an interesting one, the fact that it is sort of whizzing towards us on a timescale of 1.281 million years. I don't know whether any of us will still be around by then. We might have hot-footed it to other parts of the galaxy or succeeded in wiping ourselves out. Who knows?
Hopefully the former.
I hope so too.
Anything.
Yeah, I hope so too.
Yeah.
So just going back to one of my comments, Andrew, it is 1 arc minute a year is its motion through our sky when it's at its nearest.
Right. Could something be disturbing the Oort cloud now and us not know about it, or are we pretty well au fait with what's happening around us in this vicinity?
It is possible. The Oort cloud, the problem with the Oort cloud is it's so far away and the objects in it are so tiny that it's not really well bound to the solar system. So you don't have to give it much of a push to disturb things. And people have suggested, even giant molecular clouds in the neighbourhood of the sun could disturb the Oort cloud. In fact, I worked with some astronomers back in the 1970s and 80s who very much had that picture that there are episodic disturbances of the Oort cloud over periods of hundreds of millions of years. Every so often you regularly come near one of these giant molecular clouds, the Oort cloud gets disturbed and you get an episode of bombardment on the Earth's surface. Victor Klube and Bill Napier, my two colleagues in Edinburgh, were very big on this view. But we do have, we do have evidence that certainly there have been periods where the bombardment by the Earth has been much higher than at other periods, and not just right at the beginning. In the early history of the solar system, 3.8 or 3.9 billion years ago, there was something called the late heavy bombardment, which was a time when everything was charging around. But there have been these other periods since then where it's looked as though there have been more higher rates of cratering on inner solar system bodies, which suggests that there's been more impacts, and that suggests that maybe something has upset the Oort cloud a bit.
And I suppose it's also possible something disturbed it, 50 to 100,000 years ago when humanity wasn't a thing, and we might see the effects real soon.
Yes, that's true. Actually, 100,000 years ago, humanity was a thing, but we were different. Yeah, not quite as well in tune with the sun's neighbourhood as we were then. They just knew things were flying down at them. The point mentioned in the YouTube channel that Darryl watched, and I confess I haven't had time to watch this video, although he's given us a link to it. We'll try and do that. But that talks about events 70,000 years ago that would have messed things up.
So we could still see the effect of that.
We could, yes, that's right. Yeah, we could. Yeah, watch out for it. Watch this space.
Yes, thanks for the great news, Darryl. Appreciate it. No, thank you for your question. It was a good one. I do enjoy the what would happen if. So if you want to fire us one or two of those for episode 240, we could have a bit of fun there, because I'm sure people have got something in mind about what if. We'll look forward to those. And don't forget, again, if you do have a question, you can upload it via our website, spacenutspodcast.com, AMA link for voice, if you want to record your voice, or you can just do it through the email interface and send us the text, whatever way suits you. That brings us to the end of another program, and our first one for 2021. Thank you, Fred, as always. It's great fun and a great pleasure.
Yeah, we'll find other interesting stuff to talk about next time, and I look forward to it, Andrew. All the best, and see you soon.
Okay. Professor Fred Watson, astronomer at large, part of the team here at the Space Nuts podcast, and a special hi to Hugh back in the studio. And from me, Andrew Dunkley, and all of us, thanks for your company. We'll see you on the very next episode. Bye-bye.
Space Nuts. You've been listening to the Space Nuts podcast.
Mission complete, Houston.
Available at Apple Podcasts, Google Podcasts, Spotify, iHeartRadio, or your favourite podcast player. You can also stream on demand at Bytes.com.
This has been another quality podcast production from Bytes.com.
Radio.
Ta-da.
Well, shopping for a car?
Yep, Carvana made financing a car as smooth as can be.
Oh, yeah?
I got pre-qualified instantly and had real terms personalized just for me.
Doesn't get much smoother than that.
Well, I got to browse thousands of car options on Carvana, all within my budget.
Doesn't get much smoother than that.
It does. I actually wanted a car that seemed out of my range, but I was able to add a cosigner and found my dream car.
It doesn't get much...
Oh, it gets smoother. It's getting delivered tomorrow.
Visit Carvana.com or download the app to get pre-qualified today.
Hello, Saver. Whether you're saving for that trip to the tropics or saving for an emergency, now is the time to take advantage of Wells Fargo's savings options. Wells Fargo offers savings accounts that can help you save towards your goals. So, what are you saving for? Visit a Wells Fargo branch or wellsfargo.com/save to open a savings account today.
Wells Fargo Bank, N.A., member FDIC.